All right, let's dive into something that's literally all around us, but we almost never think about it. It's called surface finish, and it's this hidden world of engineering that quietly dictates how everything from your smartphone to a passenger jet actually works.
So, to get us started, here's a question for you. What could a super advanced jet engine turbine blade and a life-saving medical hip implant possibly have in common? I mean, they seem like they're from totally different worlds. But there's a crucial thread that connects them.
And the answer is an absolutely exceptional surface finish. Now, when I say that, I don't just mean it's shiny or smooth to the touch. We're talking about a precisely engineered microscopic texture on the surface of a part. And that tiny detail is the secret to performance, reliability, and yeah, even safety in so many things we use.
So why all the fuss about this microscopic landscape? Well, it turns out surface finish is almost never just about looking good. It's all about function. It has a direct, and I mean direct, impact on performance, how long a part is going to last, and in a lot of cases, it's fundamental safety.
I mean, check this out. The difference between a good finish and a poor one is, well, it's night and day. A good finish can slash friction, stop corrosion in its tracks, and make a part last way longer by getting rid of the microscopic cracks where failures start. A bad finish? Well, that leads to friction, rust, parts that don't fit together right, and sometimes catastrophic failure. For that jet engine or medical implant we mentioned, the stakes are incredibly high. It can literally be a matter of life and death.
And look, this isn't just some abstract concept. As researchers Konya and Kovacs point out, real-world professionals use surface roughness as a direct report card for their work. It tells them exactly how well their machines are performing, if their tools are sharp. Basically, it's a key indicator of quality for the whole process.
Okay, so if this is all so critical, how in the world do you measure it? I mean, you can't just pull out a ruler, right? We're talking about a world of microscopic peaks and valleys. So engineers have developed some seriously precise ways to put a number on it.
These are three of the big ones: RAS, RAS, and SQUAY. Each one kind of tells a different part of the story. RAS is the workhorse, your all-arounder. It gives you a great overall average. But what if you're worried about one single deep scratch that could cause a seal to fail? That's when you look at RES, which finds the absolute highest peak or lowest valley. And SQUAY is even smarter, giving you a more complete 3D statistical picture of the surface.
Now, RA is the one you're going to see everywhere. It is by far the most common. The easiest way to get your head around it is to just picture the surface as a tiny little mountain range. RA is basically the average height of all those peaks and valleys, all averaged out. It gives you a fantastic overall sense of the terrain.
So what does a good number even look like in the real world? Well, a study by Özlu and his team, who are working with high-tech titanium alloys, the kind of stuff they use in aerospace, they managed to get a surface roughness, an R value of just 0.402 micrometers. That is incredibly small.
Just how small is that? Okay, get ready for this. That is 200 times thinner than a single strand of human hair. Let that sink in for a second. That is the mind-boggling level of precision we are talking about here. It's almost unbelievable. So how on earth do you achieve that kind of precision? Well, it definitely doesn't happen by accident. It's all about carefully controlling every single variable in the manufacturing process. Let's break down the main factors engineers get to play with to nail that perfect finish.
You can think of it like there are 4 main levers you can pull. First, you've got the settings on the machine, what we call cutting parameters. Then there's the condition of the cutting tool itself. Third is lubrication and cooling. And of course, there's the material you're actually cutting. Getting a great surface finish is this delicate balancing act between all 4. That first lever, cutting parameters, is a huge deal. This is stuff like how fast the tool is spinning and how quickly you're moving it into the material. And this research confirms you have to find that just right Goldilocks zone. If you go too fast, the machine can chatter, leaving a rough surface. But if you go too slow, you can create way too much heat, which also wrecks the finish.
Next up, the tool itself. This is just common sense. Think about a knife in your kitchen. A sharp knife gives you a clean cut. A dull one just tears things up. It is exactly the same in manufacturing. As a cutting tool wears down, it stops slicing cleanly and starts plowing and tearing the material, which, as this quote nails, leads directly to a rougher surface.
Okay, and our third factor, lubrication. This chart tells the whole story. You can see the difference it makes when machining steel. The bar on the left, that's what you get when you machine it totally dry. Not so great. The bar on the right is with a cool technique called minimum quantity lubrication, or MQL.
And the difference is just wow. The right lubrication keeps everything cool, cuts down on friction, and the result is a much, much smoother surface.
All right, for our last big concept here, we need to go a little deeper. Because a part's quality isn't just about the tiny peaks and valleys you can measure on top. It's also about what's happening right underneath the surface. This is a concept engineers call surface integrity.
See, all the incredible pressure and heat from machining doesn't just carve the surface, it can actually change the metal's structure just below it. It can create these tiny, hidden microcracks or lock in internal stresses. So a part could look absolutely perfect on the outside, but be hiding this invisible damage that could cause it to fail unexpectedly later on.
So the big takeaway here is that for those really important high-stakes components, you can't just measure the roughness and call it a day. You have to go deeper. Engineers use all sorts of advanced techniques to hunt for these hidden stresses and microcracks to ensure the total integrity of the part.
And that brings us right back to where we started. This incredible power to engineer and control surfaces at a near-atomic level is really the secret sauce behind so much of our modern world. And it leaves you with a really exciting question, doesn't it? As our control gets even more precise, what currently impossible machines and technologies are we going to build next?